So today we're very happy to have Lorenz Eberhardt from IAS talking about partition functions of the tensionless string. Take it away, Lorenz.
Right. Thanks very much for the invitation, for the virtual invitation. I hope everyone is safe on the West Coast and everywhere else. So I will talk about the recent paper I wrote, which is called Partition Functions of the Tensionless String. And so I believe my first job will be to explain what exactly I mean by the tensionless string. So the plan of this talk is to first give a motivation why you should be interested in this particular string theory. And this string theory turns out to live on some ADS3 backgrounds. So I want to study partition functions of that string theory. So I will look at different backgrounds and try to compute the partition functions on those. Then we will discuss the corresponding worldsheet theories. And I will show one particular computation, namely how you compute the thermal ADS3 string partition function. So and here, until there's maybe, it's maybe not too interesting, but then I think there will be some kind of interesting surprises and physical lessons to be learned from this computation. And finally, I want to discuss or comment a little bit how this generalizes to some higher genus cases. So you can have more complicated geometries than thermal ADS3, such as higher genus handle bodies or wormhole geometries. Unfortunately, there I haven't been able to do too much of computations, so it will be more like speculative. And finally, there are some open questions. So if you're willing, I'm happy to discuss anything. All right, so let's get going. And try to see what we want to do. So usually when we compute some gravity partition functions, then say from a ADS-CFT point of view, then we always need to sum over some geometries and topologies and so on. So for instance, in ADS-CFT, if we want to reproduce some boundary partition function, then we have learned that we should sum over all the bulk geometries in semi-classical gravity. So for instance, one example where this has been made very precise recently is JT gravity. So this is the example of a 2D bulk theory and a 1D boundary theory. And say we want to compute the partition function of the boundary, which is a matrix model, on this S1, on this circle. Then what we should do from a holography point of view, we should sum over all the possible geometries. So the simplest geometry you can think of is just a disk that fills in that circle, but we can also have higher genus corrections such as this, and we have in principle a whole perturbative series. Plus, since the perturbative series is only asymptotic, there are also non-perturbative corrections to that. So that is a very nice story, but I want to ask in general over what kind of bulk geometries should we sum in some full quantum gravity, non-perturbative quantum gravity if possible. So for instance, you can ask are defects or singularities in general allowed in these bulk geometries or not, and over what class of geometries should we sum. So there's a related phenomenon that is also very nicely seen in JT gravity. So for instance, if you want to compute the partition function on two disconnected circles, then if you think of all your geometries, you have either the two disks or again high genus corrections to that, but you can also have these type of wormhole geometries. And yeah, you have probably all heard that, but here we have like a product of two partition functions since the boundary is disconnected, but on the bulk side, we can have these wormholes which destroy the factorization. And the way out of this is basically that the dual CFT or matrix model, the dual CFT is interpreted as an ensemble average of theories. So the other question I want to ask is what if we have some like one-to-one ADS-CFT correspondence where there's only a one-dimensional boundary and a unique boundary theory, which is due to some quantum gravity theory. So for instance, one example is we have ADS5 cross S5. There should be only due to super-Mills. There should not be some ensemble average or something. So you can ask how is this factorization reinstated in the full quantum theory? So this is obviously a super difficult question, so I will not be able to answer this for supremos. But what I will do is to consider some other exact stringy ADS-CFT duality that we have. And that is in many respects much simpler than supremos. So, and that allows us to a certain degree, at least, to explore these questions. So, and the ADS-CFT dual pair that I will use is on the boundary side, we have the symmetric orbifold CFT. So that's a CFT with target space being n copies of T4, and you orbifold out by the symmetric group. Maybe I should write this somewhere. So the symmetric orbifold that I keep writing. So these are just, you take n copies of the target space T4, and then you mod out by the symmetric group action that permutes all of those. So that's a valid orbifold target space, and you can consider the CFT on that. And so it has long been known that this should be dual to string theory in ADS3 cross S3 cross T4. And recently there was some strengthening of the statement. So before the statement was that it should lie on the same moduli space. And now the statement is that there is a particular point in the stringy moduli space that you can point to which it should be dual. And so this is string theory on this background, with exactly 1 unit of an SNS flux and no Raman-Raman background flux. So this goes back to some long series of papers and many more that I haven't put. So yeah, and I want to use this kind of correspondence. And so now comes the big warning signs and maybe slight disappointment. So why this is a very exact duality. So we have the boundary under control. It's essentially a free theory. It's an orbifold of a free theory. So we can compute almost everything you want to compute. And the bulk turns out to be also sufficiently simple that you can compute almost everything you want to compute. So you can really explore these questions. So the slight downside is that this string theory is somewhat removed from our geometrical intuitions. So remember that we put exactly 1 unit of an SNS flux in the background. And usually you're used to putting some huge number of background fluxes, so such that you can describe it nicely in terms of supergravity, in terms of geometry, and then maybe you consider some stringy corrections around that. But that's the regime you're used to. And this is like the opposite regime. So it's the tensionless regime, where the strings are very large and they fill up the whole of ADS. And so you're very far away from talking about some kind of point particles like the graviton or something. So the bulk theory would be highly non-local. But still, I think it's quite interesting to see what happens in this regime. So, and in one sense, it's tensionless because the strings are very large and sort of flabby, and they can wiggle around with not lots of energy excitations. But there's also another precise sense in which this string is tensionless, namely in the sense that there are many space-time higher spin fields. Usually if we put massless higher spin fields. So usually if we put the string in flat background, we have all these redshift trajectories. The spin 2 is still massless and all the higher spins have some mass. But it turns out, and if you take the tension down, then these higher spin fields become more massless.
One question I have naively, not in this setup, but in an alternate setup with a similar construct. Is this sort of like how you would construct like a Vassiliev gravity theory? Where you would have...
Yeah, from a like top-down point of view.
Yeah, from a top-down point of view.
Yeah, so I think yes, but so there are 2 issues with this. One issue is that actually the higher spin symmetry is even higher than what you want for Vassiliev. So for Vassiliev, you want like 1 higher spin field per spin, and here you have like an exponential number. Okay. And the second thing that I think you start to see also from the bottom-up approach of Vassiliev theory, you see like this non-locality. So if you would try to write down some space-time action, I think it would be extremely non-local. I have no idea how to write it down.
No, but that would be a way of thinking of this kind of construction. It's the same kind of, that's what I want to know. Thank you.
Yeah, absolutely. Thanks. Yeah, so in some sense, we're also in the unbroken phase of string theory, if you want, where all this higher spin symmetry is still unhixed. And again, I keep saying this, ADS3 is of string size. So our strings will be very, very large and not point-like. The typical string will be super large. So the goal of this talk is to consider the string on different background geometries. And here there's also a little disclaimer, because what does it mean now to talk about geometry if we don't have like a local graviton in the spectrum, but like only this non-local stuff. So while ADS3 has string size, I can still talk about the concept of worldsheet theory. So instead of, I mean, every geometry usually corresponds to some worldsheet theory. So whenever I talk about some geometry, I mean actually a worldsheet theory that describes this geometry.
So is the string coupling weak here?
Yeah, it will be weak. Yeah. Okay, and so to have a consistent string background, we need to require it to be locally of this form at least. So we don't need global ADS3 cross S3 cross T4, but we can have some quotients or things like that. And since I find it confusing and it's simpler, otherwise I will actually talk only about the Euclidean picture also in this talk. So instead of like ADS3, what I'm actually talking about is hyperbolic space, which is Euclidean ADS3. Okay, so then these backgrounds I want to look at are basically supersymmetric analogs. The whole thing is supersymmetric, but I won't bore you with the details too much. So I will mostly focus on this ADS3 factor. So the backgrounds are like SUSY analogs of hyperbolic manifolds, and all the 3D hyperbolic manifolds you can write as this hyperbolic space here, quotiented out by some group. And this group is some discrete subgroup of the symmetry group of this hyperbolic space, which is PSL2C. So these are the geometries and the theory on the geometries we can talk about. And now, since we can solve everything in this theory, we want to ask the questions, what bulk geometries do you need to reproduce boundary partition functions? So do we want to sum over all geometries, over geometries with conical defects, and so on? So this is the kind of question I want to ask. Okay, is the setup clear? This is a good point for questions. Okay, if yes, let's go on and review quickly some geometry that we need. So I'm aiming now for this thermal ADS3 computation essentially. So let's quickly review what kind of locally ADS3 backgrounds we have. And essentially, you can first distinguish them by their boundary. So they will all have some boundary. And mostly in this talk, I focus on the cases where you have a single torus boundary. So you can have wormholes with multiple higher genus boundaries and so on, but I want to focus on the single torus boundary because there everything is computable. So of course, we know essentially all of those. So there's thermal ADS3 and the BTZ black hole and more black holes. And all of those you get by taking just this orbifold group G that we had above. You just take the integers, and it's generated by a single diagonal matrix. And this diagonal matrix you can take e to the pi I t. And t turns out to be the modular parameter of the resulting.
Sorry,
yeah, please.
Sorry, could I ask just one more question?
Yeah,
it's a little late, but so you explained that you think of the geometry in the sense of theory, meaning I think the metric functional of target space coordinates that appears in the worldsheet theory.
Yeah.
But you're going to sum over target space geometries, which goes beyond the usual worldsheet formalism.
Yeah.
Right.
So yeah.
Yeah. So how? Yeah. So I'm maybe you're going to get to it, but I guess my question is how you upgrade the worldsheet formalism in which it is that you know how to define what you mean by the quote unquote geometry, space-time version of summing over topologies.
Right. I mean, what I will do is kind of naive, and I guess you will see it. So, I mean, you take like one target space, which is like thermal ADS3, and you compute the string partition function on that. You take another target space, like BTC black hole, compute the like one loop string partition function on that, and sum all of them and see what you get. It's essentially the thing you would do in semi-classical gravity, like the Maloney-Witten computation, but upgraded to string theory.
So you sum over them, and the relative phases or relative factors in that sum are determined, or
sorry, I think
I
you cut out for a second. Can you repeat that?
So you're going to sum over these individual world G calculations.
Yeah.
Or individual. Let's see.
Yeah, but well, I think the result.
Okay, yeah. Sorry. I mean, you're integrating over the target space metric ultimately, right?
Right. I mean, I need to sum over all the bulk geometries that are compatible with the boundary, essentially. So I'm fixing the asymptotic metric in ADS. But you will see that the result is actually slightly different than I think what you're imagining right now. So if the question is still there in half an hour, then please ask me again, if that's fine.
Sure. Yeah, it's just a question of how you use the world sheet formalism to do it. That's the question.
Yeah, I mean, I can formulate a world sheet around every background and try to compute corrections, perturbative corrections around that background.
Okay, thanks. I'll wait, no problem.
Right. Yeah, so for thermal ADS3, for instance, this group, this orbifold or quotient group is just a single generated by the single diagonal matrix. And these PSL2C transformations act on the boundary coordinate of ADS3. The boundary coordinate is just a two-dimensional complex plane here. So by fractional linear combination transformations, so in this case, it's just a scaling transformation. So if you orbifold now or quotient by that group, what you get is the following picture. So you get some fundamental domain on the boundary. On the boundary, the fundamental domain by that action that we had, by the scaling transformation, is that you can bring your boundary coordinate in this annulus region here. And so the full picture, boundary and bulk included, is that you have this red annulus here, which is this region of the boundary. And then this annulus extends into the bulk. And so the inner circle of the annulus and the outer circle of the annulus, they extend into hemispheres. And then in the bulk, the inner and outer hemisphere are identified. Okay, so, and if you think about this, your boundary here is indeed a torus because it's an annulus where the inner and outer circles are identified. And in the bulk that fills it in is basically the solid, the interior of the torus. So you get this picture is a picture of a solid torus. And now, so there's just one geometry like this, but it can have different interpretations. Namely, it depends, since this is the Euclidean geometry, the physical interpretation of that will change a bit what you call your time direction in the boundary. So you have different options. So for instance, you could call the time arrow, which is this option here, the radial direction. And this is now, if you slide in this radial direction, the bulk, you get this black arrow. And you see that everywhere in the bulk this is non-contractible. So your time cycle is non-contractible. And this is what thermal ADS is. Usually you construct thermal ADS as some long cylinder perhaps, and then you glue in the two ends of the cylinder. So, and your time is the non-contractible cycle of that solid cylinder. And on the other hand, you could say that your time direction should be your angular direction. That is the second option here. And then this cycle that goes around the annulus like this, if you take it into the bulk, it becomes contractible in the bulk here. And this is what is typical for the Euclidean BTZ black hole. And you could also have any linear combinations of those two cycles, and they will be more complicated type of black holes. Okay, yeah, so this is what I just said, that the physical interpretation of these geometries depends a bit on the choice of time direction. And in total, you get this SL2Z family of Euclidean black holes, which is the whole family where you can choose the time cycle to be any of those cycles of the torus. And then what actually appears in the computation is actually some super analog of this. So you're actually not taking some subgroup of PSL to C, but rather some supergroup by which you're orbifolding or quotienting. And so the ADS3 part is generated by this diagonal matrix we just had, but there's also some part that acts on the 3-sphere. And this this Z that appears here is interpreted as some SU2 chemical potential in spacetime. Okay. Then I also want to mention, since it will show up briefly later, is you can have also different geometries with torus boundary, but there are not too many of them. So there's essentially 1 or 2 other types. And one type that one can also easily compute is the conical defect. And the conical defect is exactly the same geometry as before, except that you have an additional generator. So now you have, again, this diagonal generator, and then there's a different diagonal generator that rotates the plane. So if you draw again a picture, it's the same picture as before, except that there's this additional generator that rotates the whole picture like that. So now the new fundamental region on the boundary is just this slice of the annulus. But since this part of the slice is identified with this part of the slice, you can still get a torus. And if you again trace what happens in the bulk, this picture is a Z5 orbifold on top of this. This Z5 orbifold has some fixed line in the center, and at this line you have a conical defect. Okay, so this is a singular geometry, and I want to use it to probe a bit the question about what should happen with singular geometries in this setting. Okay, and then now just a very short comment, what happens for multiple boundaries. So in principle, you can construct all your geometries that you want like this. I mean, all geometries are constructible like this, but it becomes very complicated if you have multiple boundaries or if you have higher genus boundaries. So for if you actually want multiple boundaries to investigate this factorization issue, then you need the boundaries actually to have necessarily genus at least 2. And so so for instance, how to get 2 genus 2 boundaries is actually not too complicated. You get them by quotienting by some what's called Fuchsian group. So for a Fuchsian group, you get the same moduli on both the genus 2 surfaces. If you take a quasi-Fuchsian group, you can choose the moduli independently. And the Fuchsian group is simply a subgroup of PSL2R, which sits inside PSL2C. And this one in the boundary fixes the real line. And so you will get a copy of the geometry in the upper half plane and in the lower half plane. And so that's why it corresponds to some 2-sided wormhole.
Lorenz, in the conical defect case, what is it that quantizes M? Why can we not take like an arbitrary conical defect?
You can take an arbitrary one. It's just that the arbitrary one is not realizable as some group orbifold. But in terms of, so all the smooth hyperbolic manifolds, you can write as some group manifold, some group quotient. If you have a singular one, then not all of them you can write as this group quotient. And as you say,
so it will be hard to write the world sheet theory.
Yeah, exactly. I just don't know how to write the first. Actually, for technical reasons, because of some spin structures, I actually need this M to be odd. So that's what appeared here. Yeah.
Thank you.
Yeah, thanks for the question. All right, so that's it for geometry. Is there a question about this? Okay, otherwise, let's go on and see how to construct the corresponding worldsheet theories. And so this will be kind of brief. So the idea is just that all these backgrounds that we looked at are orbifold backgrounds by construction. So if you want to take the worldsheet theory that describes these orbifold backgrounds, you should just take the orbifold of the worldsheet theory that described global ADS3. So, and now global ADS3 for 1 unit of NS flux, so this K is the amount of NS flux here, can be described in the so-called hybrid formalism. I will not go into the technicalities, but it turns out that the RNS formalism becomes a bit problematic if you put 1 unit of an SNS flux. you need at least 2 units to do it. So, but 1 unit you can describe in this hybrid formalism. And the hybrid formalism essentially deals with your target space. So the ADS3 crosses 3 part is described by some super Westermino-Witten model. Then you have your internal T4 directions, and then you put a bunch of ghosts, but these are not the same ghosts as in the RNS formalism. And this level 1 here corresponds to the amount of an SNS flux in the background. Okay, and I will be not super precise here. So actually I mean some Euclidean rotated version of PSU 1,1/2. I just don't know a good name for it. So if I write this, I mean the Euclidean version. Okay, and so now just the only comment I want to make is that we essentially know how to solve this theory. And so by construction, if you know how to solve this theory, you know how to solve orbifolds of that theory. So in particular, if you want to compute string partition functions on some backgrounds that are orbifolds of these backgrounds, all you need to do is to orbifold this PSU 1,1/2 WZW model, and the original partition function is known, and the orbifold partition function can be constructed. Okay. So that's the idea for the worldsheet theories. And so now let's see how we can use this to compute actually the thermal ADS3 string partition function. And what we will compute is actually the 1 loop bit of the thermal ADS3 string partition function. The other, yeah, we will discuss the higher loop later.
Just a small technical question. Are you allowing cusps, finite volume cusps?
Finite in cusp and what?
Well, you have these hyperbolic manifolds that you're summing over.
Yeah, but these are all smooth. There are no cusps.
No, what I mean is, you know, a hyperbolic cusp is still smooth, but it has a direction that's basically, you can think of it as Euclidean ADS with a shrinking torus cross section to the cusp as you know, that exponentially shrink.
I know, yeah, thanks. Yeah, I think I know what you mean. So yeah, there are there's one more geometry that has a torus boundary that is exactly what you say. It's like a torus that is basically a cone of a torus. So topologically, I guess that's what you're referring to. This is like the extremal BTZ black hole. And this one is a bit different because it's the quotient by parabolic generators.
It has
so,
that's right.
Yeah, so this is, I don't know how to compute because I need to go to some kind of coherent state basis to compute this orbifold because I need to diagonalize other generators. Yeah, but it's just a technical problem. I hope that one could similarly treat this case, but I don't know.
I see. Yeah, it would seem to have finite action, at least naively, because it has finite volume. But if you're going to find some precise match between the dual sides without it, maybe that's significant.
Again, it would be a bit different than what you're imagining, I think. But yeah. So again, ask me if the question persists. Thanks. Right. So yeah, we saw that we should orbifold by this subgroup of PSU 1,1/2. And if we do that, it turns out that you can write down the worldsheet partition function as I promised. And I don't want to show all the, I'm showing the details, but you don't need to pay attention to everything. So essentially this thermal ADS3 string worldsheet partition function depends on 3 parameters. So it depends on this T and Z, which we introduced in the orbifold procedure. And the T is again interpreted as the spacetime modular parameter, the Z as the spacetime SU2 chemical potential, and the tau is the worldsheet modular parameter. Now you see why I used T before. And so this is the worldsheet torus partition function, and it turns out to have some sum over sectors essentially. And there's a sum over 4 integers. And so we have these sectors, and one of these sectors can be written nicely in terms of, so the most important thing that you should look at is this delta function. So it turns out that mostly this partition function is just 0, except if there's some special relation between the worldsheet modular parameter and the boundary modular parameter. And then the rest that follows is just you have basically some phases here that depends on this chemical potential and so on. And finally, you have the T4 partition function. So it's just the partition function, the sigma model, n equal to 1 sigma model on T4. This B half, A half is just the spin structure that depends on these sectors. And you have some different chemical potential, and it depends on the worldsheet modular parameter. Okay, so yeah, one thing to look at is this delta function. So the worldsheet theory localizes actually on configuration where the boundary modular parameter has some relation to the worldsheet modular parameter. And so what's special about this relation? Remember, A, B, C, D were integers, and for this there is a covering map of the worldsheet torus. So we have the worldsheet torus and the boundary torus. If they have this relation of the modular parameters, there exists a covering map, an unramified covering map of the worldsheet torus to the boundary torus. And the degree of that covering map turns out to be the determinant of ABCD. Okay, so this this seems to be a very kind of general property of this string theory, that the worldsheet localizes always on configurations that cover the boundary of that space holomorphically. So here we see it directly by computation, essentially for the worldsheet being T2, the boundary being T2, but we have also seen it in correlation functions on genus 0 boundaries. And for correlation functions, it turns out that what is relevant is actually ramified coverings, not unramified coverings. But yeah, this is a very curious property, and I don't know what is the deep reason for this happening. And it's a localization that is kind of unusual. It's not a localization in field space or something. It's a localization in parameter space. And I cannot easily state you how this happens. So there's no Q symmetry or something that does it.
Does the delta function come from some integral over zero modes or something? Where does the delta function come from?
So in this computation, it comes, as you say, from some zero modes, and it's kind of a stupid reason. So the reason is just that the SL2C characters that appear, or representations, are all these continuous representations. So they have infinitely many zero modes. And if you sum over the zero modes, you get something like this. Let's put some chemical potential for this SL2Z, I don't know, Y, I don't know, and YN. So you just, and then you have like times oscillator part. So it's just that the zero modes, there are infinitely many zero modes, and these guys give you a delta function of Y, essentially. So yeah, so here's like embarrassingly stupid, I guess, where it comes from. But in this correlation function business, it doesn't just come from zero mode sounds like this. So, but I don't have a good understanding where it comes from. It would be really nice to find some kind of first principle proof of this. So I just know it in special circumstances. Yeah, does this answer the question?
Well, it probably does, but I didn't understand it. I just didn't understand what you wrote.
Yeah. Okay, then thanks for persist. Yeah, so in general, you would write down, like in genus 1 CFTs, you would write down all the characters on your worldsheet, and then you would sum of all the representations, right? And the characters that are relevant here is just you have some zero mode representation of your algebra, which is in this case essentially SL2R current algebra. And then you have some oscillator excitations, which are some theta functions or something. And so now the characters factorize into the zero mode bit and the oscillator, like other oscillator parts. And the zero mode bit is just that the representations, I mean, let's write them there, something like J, M, where J is the SL2R spin. And then M, the special thing here is that M runs, say, over all the integers. It's not like a finite, I mean, typically for higher values of flux, we would have representations, which are sort of what you would know from CFT, which are lowest weight representations, say, that M minus J is something like integer, a positive integer. So these are the things that sorry, I should have said. So this is like the Cartan eigenvalue, and this is like the Casimir eigenvalue, something like this. And it turns out that the only representations that appear are of this type. So these are in the continuous principal series. And so if you write down the character, what you need to do is you introduce some chemical potential for this J03, and you would sum over all the states in that representation. So you sum over all the integers and you put e to the 2 pi I. This is your chemical potential times n. I guess I should have called n and m are the same things here. Yeah, and so formally out of this, you get the delta function.
Okay, yeah, thank you.
Right. Yeah, thanks for the question. All right. So yeah, there's another property that I want to highlight a little bit in this partition function, which is the appearance of this T4 sigma model partition function, which is a bit weird if you think about it, because in string theory we should have 8 transverse oscillators. So if you just count number of oscillators and so on, you would have expected that I write something like T8 here, some 8 dimensions, like basically 8 bosonic and fermionic oscillators. And this, if I decrease the tension, it turns out that the string starts to lose more and more states. And the very rough intuition is that sort of there's not enough space anymore in ADS for those oscillating modes. So you can already see this for higher values of flux. If you turn down the number of flux, then slowly the S3 part becomes smaller and smaller and starts to lose states. So for instance, SU2 at level 1 is the same thing as S1, as some self-dual boson. So there are already less states there. Then if for 1 unit of an SNS flux, this phenomenon becomes really extreme and somehow you lose half of the oscillators. And this is somehow, yeah, please.
Sorry, you mentioned the zero modes before. In the large flux regime, at least, there were, not topologically supported winding strings, but long strings that would wind around, and they would have this continuum above a gap. What about those? What?
Right. Yeah. Thanks also for the, I haven't mentioned this. Yeah. So in general, what you're referring to are like the long strings that lead to a continuum come from these kinds of representations, whereas the short strings come from these kinds of representations. And for higher values of flux, you have both of those present. And what happens for this, if you start to decrease the flux, then most clearly you see it if you study this PSU 1,1/2 level K WZW model. So this starts to lose more and more representations. And as long as K is at least 2, you always have a continuum coming from these representations. But there are fewer and fewer of those kinds of representations present. And if you put K now equal to 1, then something a bit dramatic happens. Namely, you lose all of those representations. And of those representations, you only keep the lowest one. So you have the whole continuum, but you only keep everything is thrown out except for the lowest one. So this, technically it just follows because this guy here has some null vector in the vacuum representation, and that like restricts your possible representations of this VOA.
Sorry, I just want to make sure I understood. So there's some like number in the geometric picture, which may not apply here. There's some number of times the string winds.
It does apply, I think. Yeah, but go on.
So this m being an integer instead of you said before m would be a continuum if it were
no. What's a continuum is j.
J. Okay.
Yeah. So j in general is either. Let me find some space. J can be either real or it can be something like I guess 1/2 plus IR. So this is like the discrete series, and this is the continuous series. And this one here leads to the short strings, and this one to the continuum of long strings. And basically what happens for K to 1, that only the intersection, the 1/2, is the only one that survives.
So m is the arbitrary number of windings, but it can't have its
sorry, m is not the winding. So what m is kind of a stupid if you think from a boundary point of view, m is just how many if you have j comma j, it would be a primary state. And if you take m is just the SL2C, the conformal descendants. So it's just putting derivatives on the field or something.
Okay.
So the winding, how it's realized in terms of this algebra is a bit complicated. Is the spectral flow symmetry. So this is actually an SL2R affine algebra. And this affine algebra has some automorphism. And I don't have, let me put some place. So yeah, so basically if I make a sketch of, let me draw how the Verma module looks like. So this is the eigenvalue of the Cartan of the zero mode and the Virasoro generator. Then for these long strings, or let's first start with short strings, it looks something like this. Okay, and here you have a bunch of states. Okay, so, and for long strings, it would be the same picture, except that this continues to the left indefinitely. And so this one, which you should keep in mind is, this is like L0 in space-time, whereas the other one is the worldsheet. So from a space-time point of view, this picture is clearly wrong, because this would have unbounded energy to the left. But this is fine, because this guy is thrown out by this physical state condition. This has only positive energy bigger than 0, and it does not appear in the final answer. So what actually corresponds to these winding strings now is there's this automorphism, and if you apply it to short representation, the picture looks something like this. Basically, you tilt it around. And then there's a bunch of states. So this one has unbounded energy from below on the worldsheet. But if you fix, but for every given charge, it has bounded energy. So if you fix now the mastery condition, what you do is you basically restrict yourself to one slice like this. And if you restrict yourself to a slice like this, then again, you see that the space-time is bounded from below the energy. And this continues to hold true also if you have one of those, of these representations here where the dots continue in this direction. So also for the continuous ones. So in space-time, both the continuous and discrete ones look always like discrete, essentially, because of this tilting. And so I'm not sure whether I answered your question now with this, but this is what the winding corresponds to, how many times you tilted the picture, how much you tilted it.
Oh, how many times you tilted it, and so you're able to tilt it as many times as you want.
Right. So this one is what people call the unflowed sector. So these are like the point particle strings, basically. And if you tilt it once, then it winds once. If you tilt it more.
Okay. Oh, thank you very much. That's very helpful. Thank you. I got it.
Thanks. All right, let's go back here. So yeah, so in particular, one of these integers that we're summing over here is essentially the winding. That maybe I should say, like one is the spectral flow number. Yeah, this is what people call spectral flow, this automorphs. Sorry, I don't hear you if you want to say something.
Sorry, you pointed to the A, B, C, and D you're summing over, or?
Yeah, exactly.
Yeah,
so
one combination.
I think A is the winding in this convention.
Got it. Okay, thank you.
Yeah, and then there are more that appear basically because you do the Z orbifold. So the Z orbifold introduces more twists around the torus, and so this leads to more integer sectors. And yeah, in total, if you do the computation, you get 4. All right. Yeah, so that's it about basically this worldsheet partition function. And so let me go on and explain now what this will actually compute. So we have the worldsheet partition function. So you could just integrate it now with the fundamental domain, which we will do, and you get some result. But I want to first discuss what this result will actually compute. So the boundary, we should recall we have the symmetric orbifold, which is labeled by how many copies of T4 we take. And this n that appears corresponds to the number of fundamental strings in the background. So if you do string perturbation theory, then this number of strings is not fixed.
Actually, sorry, can I ask a very naive question?
Yeah, please.
Something that's confusing me a little is that in normal string perturbation theory, you get most of the contributions from topologically trivial maps, and then there are worldsheet instantons that are sort of topologically non-trivial in the target space.
Right.
Are you really saying that here the entire contribution comes from worldsheet instantons?
Yeah, that's essentially right. So
I mean, there are actually no perturbative contributions, and the action is actually exponentially smaller than you'd normally think.
Yeah, but the tension is also very small, right? I mean, these.
I see. So the tension goes to 0, and so the
Yeah.
large area is
Yeah.
sort of compensated by vanishing tension.
So yeah, I wouldn't say that it's exponentially suppressed, because there's essentially no suppression of the large like worldsheet instantons.
I see. If it was a finite tension string theory, though, what I said was the right intuition.
Yeah, absolutely.
Okay, thank you.
All right. Yeah. So what I want to say is that this n in the dual corresponds to the number of strings in the background. But now if we do string perturbation theory, then we wouldn't fix this number of strings. We can have any number of strings created and winding and so on. So there's really, in string perturbation theory, there's no bound. So in other words, what basically the boundary is computing it from a string theory point of view. This one is the canonical ensemble, where you fix the number of strings and you compute the partition function. But what the worldsheet computes, or string perturbation theory, will compute the grand canonical ensemble, where you don't fix this number n. So you don't fix the number of strings. And instead, what you can fix, and you can easily introduce in the worldsheet, is some chemical potential that is associated to n. So what the worldsheet actually will compute is some grand canonical partition function, which you can think of as being just all the sums of the canonical partition functions like this. And you introduce some p, which is e to the 2 pi sigma for this chemical potential.
So sorry, just so I understand. I mean, the one loop partition function, the torus in worldsheet sense is just single string states. It's tracing over single string states, right? So here instead you have in mind the entire S matrix, which certainly allows arbitrary numbers of strings to be produced.
Yeah, I'm not sure what you mean exactly by single string states. You mean like connected worldsheets or versus disconnected, or?
Well, I thought what you did before was a string one loop partition function, meaning the genus one diagram.
Right. So
yeah,
but then I can easily take exponential of that, right? And then I like create all the disconnected tori as well. That's what I will actually do.
So that's what you're doing. Okay. Just checking.
Yeah, thanks. Right. So yeah, the thing that I will actually compute is this grand canonical partition function. And it was explained actually already by Kim and Parati 5 years ago how to introduce this chemical potential. Yeah, and also that you're computing the grand canonical partition function was explained by Kim and Parati. And you should introduce the sigma on the worldsheet by adding some marginal operator to your worldsheet theory. And the marginal operator is very simple. It's just the vertex operator in the worldsheet that corresponds to the spacetime identity. So in particular, there is one operator in this duality that corresponds to the identity in spacetime, and if you and this operator essentially counts the number of strings in the background. So if you add that operator to your worldsheet theory, it's marginal, and it will introduce this sigma for you. And since it's the identity, it does essentially nothing on the worldsheet partition function. All it does is to introduce this extra factor in the torus partition function. So this extra factor just counts how much one single string is contributing to the number of strings. So it's a bit confusing that the single string can contribute like multiple times to n, but you should, as we discussed right now, there can be like these winding strings. So if this is like some time slice of ADS, something like this, and if you have this blue thing, which is some winding string, then this would correspond to 3 numbers of string charge in the boundary. So that's why a single string essentially can contribute multiple string charges. And yeah, so what it introduces is just this factor p to the determinant of ABCD. And we saw that this determinant is exactly the degree of the covering map. So the worldsheet covers the boundary here. And so this determinant is exactly the degree of that map. So by inserting this factor, and the degree is like, yeah, basically this winding number here, right? Is that clear? Yeah, so this factor like counts how much the string is contributing to n, basically. Okay, and now you can just.
Could I ask? So I understand you're computing the torus here, so maybe this question doesn't apply. But more generally, would we to study the bulk dual of the boundary theory at some fixed value of n? Do we need to fix G string and also fix the Laplace transform with respect to sigma, or?
Yeah, so this is also one issue that is very confusing for me. So what people usually say is that you have some very large number of background strings, which is n, which is larger than anything else, essentially. And now you're putting some perturbative probe strings on top of this. And since you're putting only very little of them on top of this, this will not really change n. But so this is like true in the large n limit. But you can see in the symmetric orbifold, for instance, correlation functions don't go like n to some, like they go, if you compute the 3-point function in the symmetric orbifold, it will go to n minus to the n to the minus 1/2, which is correct because n to the minus 1/2 in the, is mapped to G string. But then there are also corrections to this, which are of order n to the minus 3/2. So actually, we have somehow the situation that, I mean, the problem is that you're scattering the same things that are also creating near the background. So I don't know how string perturbation theory can properly deal with this, because somehow if you have some very long string, then you're changing the string coupling itself. And yeah, this is one thing that is confusing me very much. And fortunately, I will get around it in this talk, but in general, I don't understand. So.
Is there, I mean, are we supposed to introduce also a G-string parameter here and correlate that with the value of n, or?
I think not. I mean, in some sense, the string coupling, I think in the grand canonical ensemble is essentially 1. I mean, there's no parameter left in the grand canonical ensemble. If you look from a boundary point of view, there's certainly no parameter left. So there's no parameter that you can introduce in the worldsheet at this point.
Well, I mean, isn't there a term on the worldsheet, just like the Euler characteristic of the worldsheet that would be?
Right. That you can introduce, but so you just want to introduce this, or you want to put a linear dilaton somewhere?
I was thinking of just that, but I didn't actually understand the question. So,
I mean, usually you would put like you have like the dilaton, the space-time dilaton.
Oh yeah, no, I'm just thinking about adding just a constant to the dilaton, so just a constant piece to
right,
overall multiple
but this one I think corresponds essentially to the so in particular this would shift the sphere partition function. And so this, if you do this, I think that's essentially the ambiguity of the conformal anomaly in the boundary. So if you would add this, you change your sphere partition function. And this is like it corresponds to changing the boundary metric, I think, but I'm not completely sure about this. But there should be some ambiguity like this for sure, because I have done nothing that specifies the actual boundary metric right now. And then, yeah.
That term is a term in the worldsheet metric, right? The Euler characteristic of the worldsheet metric.
Right, but what you can do is to put some, I don't know, for instance, imaginary part of t in front, where t is the boundary modular parameter, and this will give some dependence on the. I mean, you can put some boundary metric dependent quantity here in front. Yeah, I mean, I agree. R is the worldsheet. I mean, yeah, this is just the other character. But yeah, I mean, I'm happy to talk about this more because I'm very confused about this issue.
Okay, yeah, well, yeah, please continue with your talk.
Thanks, Tom.
I'm sorry, another question about this I operator. So does it count the number of strings only on a genus 1 surface, or even if you had genus 2, this integral of I would still count some wrapping?
Worldsheet genus 2, you mean?
Both. Let's say you're considering, yeah.
This is, I mean, I think so, but it's not known, I think. So what people like, so the problem is that this operator is actually kind of difficult to compute in the worldsheet, in this orbifold, because, so for genus 1, it's still kind of fine because it's like an infinite sum, but I mean, you need to make it invariant under the orbifold. For genus 1, it becomes an infinite sum, but it's still fine. But for genus, if you have like a genus 2 boundary, then it's like a sum over some Fuchsian group or whatever. and becomes very complicated. So
Okay.
I mean, I would expect so, but nobody has done that.
Sorry, but let's say we keep the boundary topology fixed and change the worldsheet topology. Then does this operate evaluate to 0? Like if you were doing like genus 2 worldsheets in the same geometry.
So you're asking, I mean, what I had in mind is that if you compute the OP of this operator, this I operator with the vertex operator that that you have, that corresponds to, say, the W to winded sector, then you get this W in front. So which is how you see that like a winding string contributes W to the string charge. So I guess what you want to do,
because this term will be added to no matter what the worldsheet topology, right? Not just for torus.
I think he's muted or froze for some reason.
Yeah, maybe is my internet bad or?
No, I'm pretty sure it's him.
Okay. Okay, maybe we should just wait.
oh, do you hear me?
Yeah, you're back.
Right.
Okay, good.
Sorry about that. I guess that was my internet. But,
No problem.
all right. Yeah, I'm not entirely sure, Raghu. That's fine.
Okay, no problem. Thanks. Thanks.
Okay, I think I should be back. All right. Okay, I guess I should try to slowly wrap up. So maybe let me go on. Yeah. So yeah, we talked already a little bit about the sphere partition function. In principle, since we want to do a one-loop computation, the sphere partition function is of course also important, but it's a bit subtle to fix because first of all, there is a counter term like Douglas mentioned, so it should not be completely fixable. And what I will do is to just fix it by requiring boundary conformal symmetry. So I just take the boundary to have the flat metric, the boundary torus, and then you know what the sphere partition function should do. It should just essentially put this factor q to the minus c over 24 in the boundary. And you can, I just put that by hand. And you can achieve it by just shifting your this chemical potential sigma that we had by something that is proportional to the imaginary part of this boundary modular parameter. Okay, so with these two caveats in mind, so you can compute now the string one-loop partition function, finally. And what you get is, so on thermal AES3, so again, this guy depends now on T, which is the boundary modular parameter, Z, which is the boundary SU2 chemical potential, and this sigma chemical potential. So we take the exponential to account for disconnected worldsheets. We integrate this thing now on this worldsheet partition function over the fundamental domain. And now luckily we have this delta function, and this delta function essentially cancels against the integral and makes the integral computable. And if you do it, what you get is just some exponential of a bunch of like sums of the T4 partition function evaluated at different modular parameters. If this expression might seem familiar or not, I don't know, but what's written here is just the T4 partition function evaluated on all possible unramified covers, not necessarily connected, but just all the unramified covers and summed over it. And then there's some spin structure issue and so on I don't want to get into. And it turns out that this is just on the nose, the grand canonical symmetric orbifold partition function with some given spin structure again. Okay, and So similarly, you can do the computation for the other backgrounds that I mentioned. So you can do it, for instance, for the conical defect, or you can do it for the BTZ black hole. The BTZ black hole is actually very easy. You just have to replace T by -1/T, because you can get the BTZ black hole from a boundary modular transformation. But you know, since you already got the grand canonical partition function for the thermal ADS3, and you know that it matches with the symmetric orbifold. The symmetric orbifold is modular invariant. So if you send T to -1/T, you actually get the same result. So this is to say that if you take the thermal ADS3 grand canonical partition function, it actually is the same as the conical defect, and it's actually also the same as all the black holes. And all of those are the same as the symmetric orbifold. Okay, and yeah, with the caveat that you fix the same boundary spin structure. There's up to some spin structure issue. Okay, so yeah, this was very surprising to me at first that you get this. So it seems like what you need to do here is not to sum over all geometries, but just pick any geometry that you like that has the correct boundary and just compute the string partition function on that one. Okay, so let's discuss all the puzzles that appear here. So maybe the first kind of obvious or worry that you have is that you should worry about high loop corrections. So again, I haven't done the high loop computation, so I'm not sure what will happen. So if I'm guided by this localization principle, so if you assume that this localization holds true, also for higher genus worldsheets. So again, the localization means that the worldsheet Riemann surface covers the boundary holomorphically. And here the worldsheet was a torus, the boundary was a torus, and we had all these coverings of tori. So if the worldsheet is now, say, a genus 2 surface, then you see easily from looking at the Euler character that there's no covering of genus 1 by genus 2 surfaces. So that would indicate that actually the higher genus corrections are absent. Yeah, I mean, again, it would be super nice to see this prove this localization somehow, because it seems to be super powerful, but I don't know how to do it. But I can at least hope that the higher genus contributions should vanish.
Lorenz, question related to this localization property. Do you include the NS0 zero wrapping? Because your A, B, C, and D
right, the zero mapping
possible.
Actually, right, the zero mapping doesn't appear if you look at the integral over the fundamental domain. You will actually never get the zero wrapping. You can already actually see this very easily. So you know that imaginary part of T is bigger than 0, and similarly for tau. And you see that, and you had some relation like this. And these two things combined, just by brute force computation, show you that the determinant is actually always bigger than 0. And this determinant is exactly this winding. So you cannot have 0 negative winding.
I see. Good, thanks.
Can I ask another naive question then?
Yeah, please.
I mean, it seems naively based on answer analysis, though I wouldn't have expected it physically, that you're landing on an answer that looks like you have a topological A model describing your worldsheet theory, even though you started with what should have been a physical highly curved string theory. Is there a sense in which this is just the A model?
Yeah, this is something that I've been trying to somehow say for like 2 years, but I don't know how to make it precise. So I completely agree. This is how it looks like. So yeah, I mean, one comment is that it localizes on the boundary, not on the target space itself. So yeah, I fully agree with this interpretation, but yeah, maybe I should say it's not topological. Like basically ADS3 times S3 part is topological, the T4 part is not topological. So there's like parts that are topological, parts that are not. But yeah, I completely agree.
So are you able to do a comparison to the dual theory and ask about finite end corrections that aren't there because these higher genus contributions are not there?
Right. That's essentially, yeah. I mean, there are no perturbative corrections, and I think there are no non-perturbative corrections, although this is even more kind of subtle. So,
well, I guess what I'm trying to ask is, are you I mean, you had two independent sides, right, that you could use. So, and this
No.
is something you can, in other words, on the dual CFT, you can see that there shouldn't be finite end corrections directly. You can see there, or
Right there you can see that there are no finite. Yeah. So because there are
thanks.
Yeah, there are no finite end corrections. But of course, what can still happen, and what in principle I would have expected to happen, is that because in this dual CFT, you have some very long strings. So you have these maximally twisted sectors, and they correspond to strings that wind n times around the bulk. And if you remember how n was originally identified with the string coupling, these are strings that wind like non-perturbative number of times around ADS3. So essentially, you would expect that, of course, back reactions should become very important here, because the mass of the fundamental string competes with the mass of the NS5 brane that created the background. So for some reason, it seems, I mean, it doesn't seem to completely break down, and you get the correct answer, or you get an answer that matches with the boundary. And I don't know exactly why that is. What protects the spectrum from not like going crazy?
Yeah, well, large charge limits can be useful. Maybe this is an example.
Yeah, but it's not large charge. I mean, there's no charge that measures the winding, because this winding is like, yeah, but I don't know. I mean, there's not the large charge, I think, involved necessarily.
Okay.
Yeah. Right, but let's try to believe this result, and let's see what it implies. So what we already saw is that all the SL2Z black holes, as well as the conical defects, lead with the same boundary spin structure, lead to the same string partition function. And so seemingly you don't need the sum over bulk geometries. Again, geometries were worldsheet theories. So now you can ask several things. So for instance, how is this consistent with the existence of a Hawking page transition? So we learn that, so in the boundary CFT for low temperatures, the partition function is dominated by essentially thermal ADS. And for high temperatures, there's some Hawking, the transition into the black hole phase. And so here, of course, there's no transition because there's just one bulk geometry. So how can it be? And basically, what saves you is that these strings can become so long. And because the strings can become so long, they can become heavy, and the torus part of the partition function can basically compete with the sphere part. And technically, you have these sums of ABCD. We already said they're essentially worldsheet instanton sectors, not in a strict sense because you can contract them, but I will still call them worldsheet instanton sectors. And different terms here can dominate in different regimes. And so you can also, what you can argue that these contributions should basically correspond to classical geometries. So since you know you can find every state from every bulk geometry, you should be able to identify, say, the vacuum of the BTZ black hole from the thermal ADS3 point of view. And all the degrees of all the excitations are perturbative. There are only perturbative strings. There's nothing else. So for instance, if we identify the vacuum of thermal ADS3 first from the point of view of thermal ADS3, what is it? So we have a gas of spherical strings because there was a sphere partition function. And then we have the winding strings, those strings that wind exactly once around the boundary. So in this ABCD terms, it was AD is 1 and BC is 0. So these are strings that are exactly, for those strings, the T and the tau is the same thing. So they are perfectly aligned with the boundary essentially. And now we can ask the more interesting question, what is the BTZ black hole from the thermal ADS3 point of view? So again, we have these spherical strings around, and then now we can have this very long string. So we have basically this AD is 0, and now B is n. So we have one super long string, and only one that winds around ADS3 many times. So here this tau is something like minus 1 over nt, something like this. Right. So this is like a relatively classical or like a well-known phenomenon that if you make ADS3 very small, then the what used to be the black hole for higher ADS3, if you make it small, now transitions into a single long string. So basically the black hole gets replaced by this long string. And this is what is known as the string black hole transition. So it was conjectured to be true for flat space and all kinds, different kinds of regimes, already by Susskind, Horowitz, and Polchinski. And in the ADS3 regime, it was also discussed in this nice paper by Gideon Kutesov, Rabinovich, and Sever. Okay, but here we see it super explicitly, which I find kind of nice. You can also ask about the conical defect, because also the conical defect gives the same partition function. So you can ask what corresponds to the vacuum of the conical defect, and you can identify it here. And again, it's a guess of spherical strings, plus on top of this, you have many toroidal strings. Those toroidal strings wind m times around ADS3, where m was this related to this, the defect angle of the conical defect was this. So again, here you see that m should be an integer, by the way, otherwise I cannot make this identification. Okay, and again, the message is the sphere and torus can compete because the length of string is very long. And the main thing is that any state can be seen from any bulk background. But it might be that if you focus on one background, you see some states that are very highly excited from another background point of view. So I kind of view these like different backgrounds as being some different duality frames of the same theory, if you want. One more worry you could have in this computation is that there should be a Hagedorn transition. So usually if you do thermal string perturbation theory, then there's a Hagedorn temperature after which the thermal energy just blows up and the free energy becomes very large. And so basically what saves us here is because the Hagedorn transition is some large n effect. And if you pass to this grand canonical ensemble and introduce your chemical potential sigma, you regulate this problem. And you still need to be, I mean, your temperature shouldn't be too high, but the temperature, the Hagedorn temperature essentially now depends on your chemical potential. So the condition for the partition function not to blow up and for the thing to make sense is that the imaginary part of T, which is essentially temperature, and 1 over T by modular transformations should be smaller than this imaginary part of the chemical potential sigma. And if you cross here, there's some phase transition, and I don't really understand what happens. Okay, but I think in this regime you can trust it. Okay, so this is essentially what I wanted to say for the thermal ADS. Are there any questions, maybe?
I can ask a question. I mean, maybe this, I don't want to deflect you, but if you were considering the K greater than 1 situation, would you also imagine you have to introduce this chemical potential for the reasons that you mentioned?
Yeah, in principle, yes. But I think like in all the computations that were done so far, it was not really relevant because you really need to make some kind of, I mean, kind of daring computation as this one, where you disregard the normal rules of string perturbation theory. I mean, where you like consider very long strings, because
yes,
if you're just considering like so very like compared to n not so long strings, that it doesn't really matter what you do. But in principle, yes, absolutely. But okay, I think that's why it was not really discussed so much in the literature.
Thanks.
Yeah, thanks. Right. So I'm not sure how much time. I guess I'm supposed to wrap up soon, right? So.
Yeah, but you were interrupted many times, so.
Yeah, I mean,
if you can wrap up in like 5 minutes, that would be
all
5
right.
to 10 minutes. That would be good.
All right, thanks. Okay, so let me make very brief comments about higher genus case because I also don't have too many things to say and I'm more confused about it. So yeah, the main problem is that for me it's too complicated to explicitly compute. So you have these very complicated orbifold groups, and you also need to look at higher genus worldsheets because now the localization doesn't protect you anymore. So yeah, let's first discuss a single boundary with higher genus. So now you can have even more bulk geometries. So before you had some essentially like kind of manageable list. And now you can have handle body geometries, but you can also have more complicated non-handle body geometries. So handle bodies are the like interiors of Riemann surfaces basically. And the non-handle bodies have like kind of 3D handles inside of them also. So if you believe this localization conjecture, then the partition function, the worldsheet partition function should be non-zero for any genus G prime, which you can write as 1 plus an integer times G minus 1. So again, for genus 1, you see that this is always 1 again, but if you put higher genus, you can have any genus in the worldsheet. So it becomes super complicated, essentially. And but you can hope that this is still what we said is essentially still true. So you can basically conjecture that if you're able to do the same computation and compute the perturbative string partition function on these bulk geometries, then what you get is always the genus G symmetric orbifold partition function, no matter with what bulk geometry you're actually starting. Yeah, but again, I don't have much more to offer than these words. For disconnected boundaries, you can also hope that the same happens. And this gives actually nice resolution of the factorization problem. So if you assume that for disconnected boundaries, you also have that the partition function on the connected background is the same as the partition function on the same, like, so you're fixing, say, 2 boundary genus 2 surfaces. Yeah, so this is the other problem, by the way, as I mentioned before, you need at least genus 2 boundaries to have disconnected boundaries. So you cannot have like a wormhole that connects 2 genus 1 surfaces. But you can have a wormhole like this, and you can like the wormhole, if you compute the partition function on it, you might hope that it's the same thing as the product of 2 handle bodies. That again is independent of what bulk you actually fill in. If this is true, then the picture that I kind of expect is that, so these should agree, but from one point of view, factorization is kind of obvious, and from the other one, not. So this I haven't stressed actually very much. So it was not kind of completely trivial that all the partition functions agreed. So to show, for instance, that the BTZ black hole gave the same partition function as thermal ADS, you have to do this boundary modular transformation, which from the worldsheet point of view is super non-obvious what it is. And to see that the conical defect is the same thing as thermal ADS, you do some additional orbifold, and this orbifold sort of scrambles around your states, and in the end you get again the same spectrum. But it's not completely obvious for me that it always works. So I kind of, yeah, so it's not supposed to be obvious. So what I think should happen is that in the connected background, factorization is somehow obscured because your states are arranged in some weird way. And in the disconnected background, it's obvious. It's manifested, it factorizes. So this is the kind of rough picture that I have how the factorization should be restored for this for this case where you just have a single boundary theory and not an ensemble. All right. So yeah, there were already many questions, but let me add a few more. So yeah, so the kind of major question I have that why don't we have to take into account back reaction? I think this is one of the most important ones, because if you don't answer this completely, then I'm not completely sure whether you should even trust this computation maybe. And you can also ask about other non-perturbative effects like d-instantons. From a boundary, they're not there, but you should still show from a bulk point of view that somehow there are no d-instantons that contribute. You can also ask about non-saddle contributions. So for instance, in 3D gravity, you can actually compute the wormhole that connects two genus 1 surfaces. So there's a wormhole of topology T2 times an interval. The trouble is just that this is not a solution of gravity. So there's no, this is not a saddle. So in gravity, you can still compute, even though you don't have a saddle. It was done by Kotler and Jensen. But in string theory, I don't even know how to set up the computation if I don't start expanding around some saddle. And you might also try to sort of identify these non-saddle contributions. If they're already accounted for, then you should be also able to identify them somehow in the final partition function. And yeah, I don't know how to do that. maybe. So what I also want to mention is that it sounds incredibly hard to do the string partition function on the Euclidean wormhole, say, but actually the answer is relatively simple. I mean, the answer is always the same thing. If you're computing some grand canonical partition function on the symmetric orbifold, the only thing you have to do is you have to sum over all the covering surfaces. So I told you this for the torus already. The formula that I wrote, it was just the sum over all the covers of the original torus. And you just put p to the degree of that cover. The covering surface is not necessarily connected. You just all the covers. And then you compute the partition function of T4 on this cover. So this formula is always true for all genera, for all surfaces, and so on. So I just want to point out that the answer is not super difficult in principle. So I believe that it should be possible to reproduce it from string theory. And I hope we could perhaps also learn something about string perturbation theory in the process when we do this computation. Okay, but yeah, obviously you cannot like just stupidly do some orbifold procedure. It would be too complicated. Yeah, then you can ask what, so this is some kind of cute story, but it's not clear to me how this will carry over to some other backgrounds, larger flux, deformations. So for instance, there's a deformation away from the symmetric orbifold point, and that you can turn on. And it would be kind of interesting to see what happens. And some parts of this should be spoiled, I think, because this deformation connects you continuously to some higher values of flux. And at some higher values of flux, there are certainly black holes, and they are not equivalent to long strings. So somehow you should see how exactly this string black hole transition gets broken. Yeah, another question that I have is how the Lorentzian picture works. This was obviously all Euclidean, so there should be some interesting Lorentzian interpretation. And finally, maybe, yeah, I told you we're essentially talking about this un-Higgs phase of string theory, where the highest spin symmetry is unbroken. And I sort of have the suspicion that there should be some gigantic symmetry that controls all of those partition functions. And maybe this gigantic symmetry is just, this higher spin symmetry is just powerful enough to completely nail down the answer. And so, yeah, basically that's why everything agrees. All right, I think I kept you long enough, so let me thank you for your attention.
Thank you, Lorenz. Let's give a round of applause. It was a really nice talk. Are there more questions beyond the many that we already had?
I can ask a kind of quite a vague question. It relates to some of these, well, some of the open questions and the higher genus connected wormhole. Do you have any like even vague guess about what part of the disconnected geometry calculation, might start resembling the wormhole geometry in the same way that a long string kind of resembles the black hole? Do you have any kind of even hint of, what you're doing in the disconnected geometry?
Yeah. I mean, it should be obviously some kind of diagonal piece of the disconnect. That's the kind of
obvious
right. Answer, right? But
yeah, but yeah, okay.
I mean, yeah, I guess it would. There's always some sum over instantons, and I guess roughly speaking, the diagonal part of that sum over the instantons, I would expect to be the wormhole, the vacuum of the connected part. But
okay,
I don't know whether that's true, but
yeah, okay. Okay, thanks.
Yeah, sorry.
I'll struggle with that too.
Any more questions? All right, let's thank Lorenz again.
All right.
Thank you, Lorenz. It was really nice.
Yeah, thanks very much. That was a very interesting talk.
Thanks.